have about 2 minutes.
For when you're trying to find the area of the shaded regions or graph, is this alpha and that's beta?
That's, well, the figuring out the angles is the hard part. So what you need to do, this is probably 0 because it's going straight to the right. So if you plug in 0 here,
Oh, it's 0 pi.
so you get, if you plug in 0, you would get 3 for R. So in the 0 direction, it goes 3 and plots a point. So that is 0 right here. This is probably pi because it's going straight to the left, but actually plug it in here, see that R would be 1. So it's going 1 in the pi direction. So this is 0 to pi this time. But sometimes it can look like that and not necessarily be that. It just depends on the function. So
that's how you check.
yeah, that's why you need to actually plug it in and make sure that it's what you're thinking it is. Have a good day.
Bye, Mr. Tapperton.
Hey, thank you. You didn't fall asleep on me, did you? You did. You okay, bud?
No, I'm not.
Okay. Well, I asked and he didn't say anything, so.
I'm putting my left hand over the board. And I was I did it. I did okay. When I watched it, I can. I was like making. I was like, yeah, more of a big part. You would too. I just have to mark the sheet again. Oh my gosh, I ran. I forgot. I thought I had my ID. I didn't. Uh-oh.
There's the stickers even taken
I
off.
can't breathe. So they made me walk around the whole building. Oh my gosh, really? Get my ID and then have to come up here. I'm gonna go to the home office to get that. Okay, so you're walking, I thought. I got here early, so I was like, oh, I'm ready. I get to pull out the payments early. You lost already? You can go home. I think I just fell.
All right, good morning, guys. So if I did not get your 36 last class, I would like that today, please. Oh, I've already got a few of them up here. So 36 was on the nth term test for divergence. Okay, so this is a B week, so I'll see you today and tomorrow, and then you'll be caught back up with my A-Day classes. And so today we're going to look at 10.4, which is called the integral test for convergence. And it's not particularly a hard one, but it's a little more annoying because you do have to do some integration, as you could guess by the name integral test. So depending on how well or how comfortable you are with integrating, it's probably going to dictate how much you like this test or don't like this test. But then tomorrow we'll do 10.5, and that will be like the first chunk of Unit 10. So next week, Tuesday, we'll review 10.1 through 10.5, and this time next week we will have our first Unit 10 quiz. Before I forget, just in case I haven't said it, I need you guys to also realize that the stuff we're doing right now, 10.2, well 10.1 is just kind of random stuff, but 10.2 was geometric series, 10.3 was the nth term test for divergence, 10.4 today's is integral test for convergence, and then tomorrow we'll look at the harmonic series and p-series. Harmonic and p-series is very easy. But what I need you to understand is that, yes, we'll have a quiz on that stuff and you need to know that stuff, but when we move on to 10.6 after the quiz, we're still going to be using these things. This is kind of our foundation that we're going to build upon. In fact, 10.6 is called the comparison test, and you will be comparing it to these things. So if you don't know from these skills whether something converges or diverges, you're automatically stuck when you're trying to compare it because you don't have anything to compare it to. So I know you guys always put out your best effort, so I appreciate that, but I'm also just trying to give you that heads up that really understanding it well will pay off. Okay, so 37, integral test for convergence. Okay, so for this one, we do also need to do this proof in the middle, and most of the time I tell you guys that the proof, is good for you to see it, and sometimes it can help you kind of understand why something works. I can tell you that this proof, some of the questions on today's practice are based on if you understand parts of the proof. So make sure you put in your best effort there. But really, this test, you need to know when you can use this test. So to use an integral test for convergence, your function has to be positive, continuous, and decreasing. And then you need to add some words here. Over the long run. because if a function is positive, continuous, but increasing at first, but over the long run it's decreasing, positive, and always continuous, that's still okay. Over the long run. And then the second thing, these are the requirements, but what's heavily recommended is that you can integrate it easily. That's not a requirement, but this method we're going to have to do some integration. So if it's not something to integrate easily, it's probably not this test. Okay, so assuming it meets those conditions, if we take the series and it's always positive, we never have division by 0 to make it discontinuous, and we can see that each term gets smaller and smaller and it's decreasing, then the answer to our infinite series will be the same as if we integrate from this to this. So probably 1 to infinity, but it really can be anything, so we'll just say. And then we think of a of n, which is the sequence here. We just think of it as a function, f of n, but basically the same thing. So basically we're going to do this work, and we're either going to get a number, meaning that it converges. We're going to get infinity or negative infinity, which means it diverges. And that is going to be the same as the answer to our infinite series. So if we integrate, see that it converges, the infinite series also converges. If we integrate and we see that it diverges, then the infinite series diverges. This test is not good enough to tell it what it converges to. It only can determine whether something converges or diverges. So this is really the bulk, knowing when to use this test and basically how to use it. Okay, so this is the proof part. And again, it's not that you have to be able to replicate the proof, but you kind of need to understand the proof. So they did two sides here, and I'm going to do both of these at the same time, kind of discussing them. So this is easy to get lost in, so do your best to follow along with me here. But there's two pictures because one is a left Riemann sum. Notice they took the left xmost value and drew to the right. And then the other side is a right Riemann sum, where they took the rightmost x value and drew to the left. So that's the two things that could happen. And if we think of this, so if we're doing a left Riemann sum, I need all of these, well, let's just label these. This would be when n is 1, n is 2, ... till n is n, and then this would be n plus 1. Over here, a is 1, a is 2, ... till you get to a sub n, and then this is a sub n plus 1. So when we're talking about this value where it's hitting the function, this is when n is 1, so this is like a sub 1, it's the first term, or you might think of it as f of 1. This is when n is 2, so this is like a of 2 or f of 2, same thing. Whereas over here, we're actually going to start with the second term, because the first term doesn't hit the function, and this is a right Riemann sum. So we're going to start with the second term, and then the third term, etc. Now when I use this one in a second, since I'm doing left Riemann sums, I'm going to quit at this one. You're going to wonder in a second why I use n on one and n plus 1 on another. But left Riemann sums, I want the far left. So I'm going to go till I get to a sub n. But on the right Riemann sum, I'm taking the rightmost values, so I'm going to keep going till I get to a sub n plus 1. And that's why I labeled the next one after a sub n. Okay, so basically what I want to do is if I think of this as an infinite series where I start off at 1, where n starts off at 1, or an infinite series where n starts at 2, but I go to n plus, this should be n. This should be n for just a second. I stop at n, it's the leftmost x value as far as I go, and then over here I stop at n plus 1.
Do we capitalize the n or no?
Yeah, because it's really not the same as this n, so I'm trying to distinguish a little bit. Okay, so now what we are trying to do is we're trying to think of, well, if I integrate this, I'm trying to compare this to integration. We know integration gives us the exact amount of area under the curve. So if I integrate this as a function, dn, with respect to n, so basically, you know, a sub n and f of n are the same thing, so it's just a different way to write that. But if I do this one from 1 to, I would like this to go to infinity. Actually, leave it for n for a second. We're going to come back and change that in a second. But I'd like that to go to n. So I'm going to compare these two. So this left Riemann sum, is it giving us an overestimate or an underestimate of the actual area?
Overestimate.
Right. This stuff makes it be an overestimate. It's an overestimate. So which one of these is bigger then?
It would be the left one.
Right, the left one's bigger. So if it's a left Riemann sum, we are sure that this actual sum, if you took this value plus this value plus this value plus this value, would be bigger than the function. Whereas over here, this is an underestimate. We're missing area. So it's going to be the opposite. It's going to be less than or equal to, if I integrated from 1 to n plus 1. I'm going to n plus 1 on this one. Again, this one I went to n, this one I went to n plus 1. It's really not that important, but again, I'm just taking the leftmost value here, so n is as far as I can go, and over here this was a right Riemann sum, so I can take the rightmost value.
Wait,
which
do
was,
we not start at 2 then?
yes, we should. We should. Thank you. Okay, so now here's the important part, how these, we're going to combine these into a single statement. So here's our two possibilities. Either the exact area under the curve is less than what we get from the infinite series, making the infinite series an overestimate, or it could be a right Riemann sum where the actual area is an overestimate of the infinite series. So the area under the curve is bigger than the infinite series because there's stuff that we're missing. So if I try to combine these into one statement, one thing that I will do here, and actually I should have started off, this should have been at 1 for just a second. What I want to do is on this side, I'm going to add the first term. So if I add the first term to this side and this side, now I don't want to start at n equals 1, I want to start off at n equals 2 because I've already got the first term, I'm adding it. So what we can do,
Would the plus a1 be out like the side if we have enough room?
yes, it would just be a number. Okay, but really what I want is I want to do this forever. I want to go to infinity. So let's make this go to infinity, this go to infinity. This could go to infinity plus 1, but infinity plus 1 is really just infinity. So again, I said all those were really going to change in just a second. But what I'm going to do is I'm going to try to sandwich this in the middle. Now, starting at 1 or starting at 2 honestly doesn't really make a difference, because if you're talking about if something converges from 1 to infinity, it's going to converge from 2 to infinity. If it diverges from 1 to infinity, it's going to diverge for 2 to infinity. There's nothing happening between 1 and 2 that changes whether it converges or diverges. Oh, sorry. So in the middle, I'm going to put my infinite series. Still, from 1 to infinity. So this is what we generally work with. But over here, it's greater than or equal to this. So I'm going to try to write this as a compound statement. I'm using this one right now. This is greater than or equal to integrating from 1 to infinity of f of n dn. And then over here, this infinite series was less than or equal to, and again, it doesn't matter if this is 1 or 2. I'm going to put it as 1 because I want you to see that these are all the same. 1 to infinity of f of n dn plus the first term. Remember, I added the first term there. So this last statement is basically what you need to be able to use out of this. This infinite series that we're doing, regardless if it is an over or under estimate based on a left Riemann sum or a right Riemann sum, it has to be greater than or equal to integrating from 1 to infinity, or less than or equal to integrating from 1 to infinity plus the first term. So basically, if this goes to the number 7, then this is going to go to the number 7 plus something, which is also a number. So let's say it's 10. If this goes to 7 and this goes to 10, that guarantees that this converges, right? 7 and 10, 7 to I'm just making up numbers, 7 to 10. Those are nice finite numbers. If this goes to 7 and this goes to 10, this is something between 7 and 10, but that converges. It's going to a number. So, also, if this diverged, if this goes to infinity, then this certainly goes to infinity, because this is the same thing plus a number. So if this goes to infinity and this goes to infinity plus 7, then we're guaranteed that this also goes to infinity, right? So basically what this inequality is trying to say is if this converges, and therefore yours also converges. If these are both going to numbers, then this has to go to a number. If these both diverge, or if this diverges, if this goes to infinity, adding a number to that makes it go to infinity, and if this is going to infinity, if this is going to infinity and this is bigger, then this has to go infinity too. So that's why it's a proof. If this stuff is converging, this also converges. If this stuff diverges, this diverges. So that's what we wrote down up here, but that's trying to show why. Now,
Oh, up there. Oh, wait, no, never mind. Back down. Yeah. For the total equation, bring it all together. It was n plus 1. Wait, do we replace the 2 with 1 up there?
I did,
N
yes.
equals 2.
Yeah. Again, part of it is I'm trying to get you to see that whether you start off at n equals 1 or n equals 2 doesn't change whether this converges or diverges. It's still going to converge or diverge. It would be one less term, but that one term doesn't dictate an infinite series. It's more about what happens over time. Okay, now I know this part always seems a little bit confusing, but wait till you get to the back page when you can see how they're going to ask you to use it, and it's quite a bit easier to use than you would expect. The very, very last question is 1, but don't worry about that right now. Let's look at these couple of examples, because this is what's actually going to be used. Or this is what the bulk of the questions are. So basically, I see this, and honestly, keep in mind the things that you've learned. In Unit 10, it's not that any one lesson is tough. Geometric series are pretty easy to learn what they are, when they converge, and what they converge to. The nth term test for divergence, knowing what it tells you and how to do it, is pretty easy to do as long as you can do limits. Doing this test is not super insanely impossible or anything, but over time what becomes tough is knowing which test to do. So when I look at question 1, this is not my first go-to. I don't want to integrate every single question. This is more work than's needed sometimes. So for that reason, I tried to find an escape route. If I can find an easier way, I'm going to do that. But at some point, if I can't think of anything else, I'm going to consider this test, and I'm going to think, is he always continuous? Is he always positive? And then what's the other requirement?
Decreasing.
Decreasing. Now, if you don't know if it's doing all of those things, one way you could quickly check, well, first off, how is something not continuous?
If it equals, or if the denominator equals 0.
Okay, so couldn't n be 0? Wouldn't this be, why can n not be 0? Good, because we're starting at 2. If we're starting at 2, we never divide by 0. If you make yourself write out the first couple terms, here's the first term, here's the second term, I can see that these are always going to be positive, and I can see that they're getting smaller each time. So the requirements are met, but if the requirements are not met, then you're doing a bunch of work for no possibility of a gain here. So integral test for convergence says, okay, we'll integrate this then. Integrate 1 over n natural log of n dn and integrate it from here to here, 2 to infinity. So, like we had to do the first week of school, this is an improper integral, so don't leave this infinity. Make it the limit as b goes to infinity. And then, of course, this is going to vary. So I know there's at least a couple, at least 2 or 3 today that you have to do u substitution on. And there's one you have to do integration by parts on. So that integration's harder, so that makes it a little bit harder. But this one is a u substitution question. If you picked this out to be your u, du would be everything else you need. So this would be 1 over u du. Don't forget to update your bounds. 2 is when you're using n values, but when n is 2, u is natural log of 2. When n is b, u would be natural log of b. So make sure you update those bounds when you do u substitution. But now that I have rewritten it, I can see this would integrate as natural log absolute value of u. I want to evaluate it from natural log of 2 to natural log of b. So notice this limit, just along for the ride for a while. Plug in this first, you get natural log of absolute value of natural log of b, which sounds pretty crazy, but it's fine. Plug this in, natural log of 2. Okay, and then when I try to plug in infinity in for b, what does all of this go to?
Infinity.
Okay, and then this is just a number. So infinity minus a number still goes to infinity. So what we just did is we figured out that this integral diverges, therefore the original question diverges. I know the integral diverges because it went to infinity or negative infinity. And again, I did all of that because I know that this infinite series does the same thing. Now again, this one's a little bit harder because U substitution's a little bit harder. There's more steps to it. Question 2, considerably easier, but don't just jump into it. You need to force yourself to think about the conditions. I know if I asked you what the 3 conditions are, you could probably tell me without looking at your paper right now, but you're not going to be able to do that in a week or 2. So try to force yourself to say, is it continuous, positive, and decreasing? Make yourself think about that. If we're only starting with n equals 1, you're never going to get division by 0. If I write out the first few terms, I get 1, a 4th, a 9th. They're always positive and they're always decreasing. So those are the must happens. And then the recommended is if this is easy to integrate. If you can see how to integrate 1 over n squared from 1 to infinity, then this is not a bad test. If it is impossible to integrate or just a pain to integrate, I would only do it as a last resort. But you're actually going to learn some, again, as we do these things, you learn more tricks. So this is actually a P-series, and I can tell you right now, because I know P-series, just glancing at it, that this is going to converge. So that's one of the things we'll talk about tomorrow. So you got to do the integration. Again, it is good for you to have to practice this improper integral because it's been a while. But raise the power by 1, divide by the new power, evaluate from 1 to b. You would get negative 1 over b minus a negative 1. So what does all this mess come out to be?
1.
Okay. So what? Who cares? What does that mean?
It converges.
Right. Since this converges, this also converges. That's what we just figured out. Does it mean it converged to 1? We didn't talk about that, did we? It does not mean it converged to 1. If this converges, we know this converges, period, end of statement. Just because this converged to 1, this does not necessarily converge to 1. In fact, the only test that you have learned thus far that you can figure out what something converges to is the geometric, the first term over 1 minus r. Nth term test for divergence doesn't tell you what something converges to. This doesn't tell you what something converges to. And even the P-series we talk about tomorrow doesn't tell you what it converges to. Just most of these tests are only good enough to figure out if something converges or diverges. Does it grow forever unbounded, or is it bounded and eventually going to settle on something? So again, 95% of the hassle and work here is going to be the integration steps. But you guys are pretty good at integration. It's just that it's been a few weeks since I've made you do any integration by hand. I will say that on the practice questions, this first one, I'll just give you a warning because I wish they wouldn't do this on the first one. To integrate this first one, you will have to do integration by parts. So if I was you, I'd probably skip that one. It's just a little more involved. But I would skip it and do it later. But if you want to do it up front, just be aware that it's integration by parts, so it's going to be the hardest of any of these to integrate, I believe. Okay, so go ahead and try to get a few of these under your belt. If you kind of scan through the whole assignment, we've got 13 questions total, but there's only 6 before they're like short answer, multiple choice type. So the first 6 take a little bit longer, and then the questions after that are pretty conceptual, where you don't need to work out a bunch of steps. So, get done what you can, please, before lunch, and then when we come back, you will have the whole second half of class to work through and finish this. So this is certainly one that you should be able to finish up in class today and avoid having any homework.
You just go up